2, 1. Alright, here we go. As promised, a pre-recorded lecture for Math 317. Gonna follow up what we were talking about in class yesterday. We have introduced the notion of a basis of a vector space, and now we're going to talk about the dimension of a vector space, a concept related to bases, as you can imagine. Alright, well, let's do a quick little recap of what we proved in class and set up. So, recall a basis for a vector space is combining the two previous topics into one concept. So, we talked about the span of a vector space, the smallest subspace containing the given set, and we talked about linear independence, where scaling and adding giving us a trivial linear combination can only happen with trivial scalars, and so a basis is smashing those two objects together. We span and we're linearly independent. And we've already encountered such things, so we recontextualized a fact we knew about the standard basis elements for Rn, which again are the elements that have 1 in the corresponding location and 0 elsewhere. We already knew that these things span. We didn't say they span when we first talked about them, but now we know. And we also verified that they are linearly independent. This is a basis for Rn, as we now know, and it's called the standard one because, I mean, it's pretty nice. It's just zeros and ones in appropriately chosen locations. But as we noted, there are other bases for Rn that you might be more interested in, depending on whatever your problem is you're working on. Okay. So, and we pointed out further, not only does Rn have a basis, but in fact every vector space must be equipped with a basis, as a consequence of the following effect. If you have a list of linearly independent things, and you can find something that is not in the span, so it is not a basis, it's just a linearly independent set, then it can be made into a larger linearly independent set. And so we noted that with some hand-waving, you can prove that every vector space has to have a basis, because every linearly independent set can be inflated, can be made larger if it fails to span, so it stands to reason that continuing that process indefinitely should eventually yield a basis. Now, the continuing indefinitely, there's some hand-wavy stuff there. As we noted, there's some more sophisticated math tools, such as Zorn's lemma, that can make that argument a little bit more rigorous, but it turns out that if you accept such mathematical tools, then yeah, you can get every vector space as a basis, which is our operating assumption. But as we're going to see, the unique thing across all bases is the number of elements. We already kind of mentioned that Euclidean space has other bases that are sometimes more useful than the standard one. We gave an example in R2, for example. We will now prove the main tool to help us verify that, in fact, yes, the number of elements is always the same across any pair of bases. All right. Okay, so this is a consequence of the following result. I have always seen this called the dimension theorem. I have always referred to this as the dimension theorem. Some books don't even give this a name. They're just like, oh yeah, this is true. Other books will call it the dimension theorem. The dimension theorem is also used for something we're going to call the rank nullity theorem. And in that case, I think that's an egregious use of the term. Rank nullity theorem is its name. We'll talk about that one in class, the back half of this week. But anyway, let's digest what the dimension theorem is saying. It's saying that if you have a list of elements, and you have another list of elements in the span of that list, and you know that the things in the span are linearly independent. So note, these we do not know anything about other than they exist. These we have the linear independence requirement on. Then it's got to be that n is less than m. So, in other words, the number of linearly independent things in a span is bounded above by the number of elements used in the span. And if we're thinking about Euclidean space, this should hopefully make a little bit of sense, right? So, for example, if we have 3 linearly independent things, and we were thinking about, like, 3 vectors or something like that, then there's no way that could have lived in the span of two things, right? The simplified span technique we saw, like, yeah, if you reduced it down to two vectors that made your span, then finding three linearly independent things doesn't seem possible. Right, our general math intuition tells us that, yeah, this should be true. And indeed it is, and we will prove it. Now, before moving on, I will note that this is the finite version of it, and again, as mentioned, we're going to kind of focus in on the finite dimensional sort of case, so bases only consisting of finitely many elements. It is worth noting that there is a general version of this, because again, span and linear independence are not restricted to finite lists, they can be defined for subsets. Their definitions get a little janky, but you can still work with them. And the analogous version of the dimension theorem holds. It is a hell of a lot harder to prove, though. Oh my god, let me tell you, the proof of that is, it's effect. You'll see, the proof we're about to do really only flies in the finite case, because we're going to create a matrix. And for the general case, it's a mess. Oh my god. Let's just leave it at that. Anyway, so how do we prove this? Well, let's just unravel what we know. We know that the v's live in the span of the w's, so we know each v is a linear combo of the w's. So for each vk, I can find a list of scalars so that I can scale in at the w's and get them. And oh, hey, look, I have, oh, that looks a lot like a column of a vector of a matrix there, right? Hey, k is fixed, and then I'm running for the rows. Oh yeah, how about I make a matrix? It's defined by the scalars that were used to get v as a linear combination of the w's. All right, so I want to prove that n is less than m, so that's our goal. And right now we've unraveled this part of the hypotheses. I haven't used linear independence yet, and I bet the linear independence is why this happens. So let's go ahead and suppose that m is less than m. So if that's true, then I have a matrix with a larger number of columns than I do rows. So if I were to look at the homogeneous linear system, ax equals 0, I have more unknowns than I do equations, right? I have more columns than rows, so there are more unknowns than there are equations. We know this always has a solution, and if I've got more columns than I have rows, then not only will this have solutions, I can ensure that I can always find a non-zero one. There's a few ways of arguing that. Note that the echelon form of this basically is only going to ensure that at most m of the unknowns are going to be able to be locked down, but I have more than m of them, so some of those are going to be free variables, so they can just be whatever the hell you want them to be. Alright, so because m is strictly less than n, I can find a non-zero x, so this works, and I bet that's going to not jive with my linear independence, because, hey, I've got a matrix who's got a non-trivial null space, which we know is related to linear independence. Alright. So, we'll now let alpha and alpha n be the elements of xn. I'll scale all my v's by alpha, so take this equation and just scale this by alpha k. That'll give you this beautiful list, which I can then add up. I got this, oh, look, I got this beautiful linear combo of my v1 to vn. Man, it'd be bad news if this was equal to 0. And upon closer inspection of these things, we know that a times x is equal to 0, and if you look at the jth entry of this vector, oh, wouldn't you know it, it just so happens to be the coefficients on all these w's. And hey, that means this is a trivial linear combination. That should be the 0 element of the vector space, not the number 0. Let me quick fix that. Alright. And, oh, what do you know, then our hypothesis ensures that all those scalars are 0, because v1 to vn was linearly independent, but that means the vector x was 0, which is contradictory, because we already pointed out that we have non-zero things, and so it's got to be that n does not exceed m. Alright, so, we have the dimension theorem in the bag. Note we used matrices to pull it off. And again, like I said, this is the finite version. There is an infinite dimensional version. Who cares? Trust me, bro, it's true. Alright, with this in our back pocket, we now can rattle off two facts pretty quickly that are going to be very nice when it comes to working with elements and linear independent, and determining their linear independence. So, for example, if I have a set, if I have a list of n things, and I have m things in the span, and I know the number of things in the span exceeds the number of elements I used to create the span, then it's got to be that these things are linearly dependent. Note, if they're linearly independent, then the dimension theorem would bound them above by n, but my hypothesis here is that I have more than that. So they have to automatically be linearly independent. So, as a nice consequence, if we're in Rn, which we know is spanned by n things, if your number of elements in your list exceeds n, then you have a linearly dependent list. So, for example, here's 3 things that lives in R2. R2 is spanned by 2 things, so we know that this must be a linearly dependent set, because if it was linearly independent, well, then we'd violate the dimension theorem. So that means I can find A, B, and C, so I can scale and add them up and get 0, and they're not all 0. And it's not too hard to verify that -1 to -1 is going to do the job. Alright, nice. So, this is going to be a very powerful and useful fact for us. If you have a list of elements in Rn, and you've got n plus 1 or more elements, we immediately know you're linearly dependent. And on the flip side, if you are in a set that has a basis consisting of n elements, then any linearly independent set with the same number of elements will also be a basis. And vice versa, if you have a basis, then its number of elements has to be n. And there we go. So, prove the first fact. Let's say we have our linearly independent set. We just need to know that it spans. That's what ensures that it's a basis. If it doesn't span, I can find something, but as we know, we can then make a larger linearly independent set, but then that's going to violate the dimension theorem, because then I'll have n plus 1 linearly independent things in a span made using n elements, which we know we cannot do. If you are in the span of a set of n elements and you're linearly independent, you cannot have more than n things. Alright, that takes care of point 1, and then point 2, well, x1 to xn is in the span of y1 to ym. The x1 to xn by hypothesis are linearly independent, so the dimension theorem bounds n above by m. And a similar argument applies because my y1 to ym is assumed to be a basis, and they live in the span of the x1 to the xn, and that will then get m is less than n, and so m and n must be equal. Nice. Alright, so with these facts in our back pocket, we have a couple of fun little consequences. So, here is a list of 3 things in R3. 1, 2, 3, 4, 5, 6, 7, 8, 10. And it doesn't take too much effort to verify this is linearly independent, so remember, for a list of vectors in Euclidean space, smash them together in a matrix and get its row-reduced echelon form. If you get something other than the... so if you get a row of zeros, then you know that you're going to be failing to be linearly independent. Right? Look at the null space formed by the matrix. If there's non-trivial things in there, then we know we are linearly dependent. But we can verify that this has to be linearly independent, and thus, since it has 3 elements, it automatically is a basis. So note that tells us we know the span is all of R3. I don't have to prove that. So this is actually a very nice fact about vector spaces. If you know the dimension of your vector space beforehand, if you know how many things have to be in a basis, then you actually never need to prove the span part of it. You just need to verify you have enough linearly independent things, and span is for free. We're going to make use of that quite a bit. It's a very powerful fact. Alright, we can push the previous point a little bit further. Here is 2 things, and you can verify very easily these are linearly independent in R3. And note there's 2 elements here, and we can turn it into a basis by throwing in something linearly independent. So we know that this can't span, because if it did, that would mean it's a basis, but that would mean you'd have a basis of 2 elements in R3, which you know is not possible. So you can always extend this set. We can find something to add to it that would make it linearly independent, which would then turn it into a basis, because it then has enough elements to match the standard basis for R3 that we already have access to. In fact, in general, this is true. If you have a linearly independent set in any vector space, then there is a basis that contains the original. And this was and the same proof of our kind of hand-wavy argument of why every vector space has a basis. We started with the linearly independent set, the empty set. So you could start with any linearly independent set. If it fails to be a basis, you can add more elements and make a larger linearly independent set. And then, again, our sort of hand-waving of indefinitely repeating that is going to ensure that you have a basis. So we're going to use this fact quite often, where any linearly independent set can be extended into a basis. And finally, as noted, the last point of the previous proposition, so not this one, but that one right there, that ensures that any two bases have the same number of elements in a finite case. It's true if you're infinite as well, but again, the proof is a little bit more wonky because you gotta allow for general subsets, and it's not any more difficult than kind of what we've been seeing. But as I mentioned, the proof of the dimension theorem for the non-finite case is a little... depending on how you approach it, you're going to have to pull out a big gun to take it down. Either Zorn's lemma or the marriage lemma or theorem or whatever it's called is one way of getting it as well. Anyway, so this allows us to define the dimension of a vector space to be the size of any of its bases. So in the finite case, that's literally just counting how many you have. For infinite and beyond, then it's cardinality. So if you've got countable or uncountable, and then the various stuff involved there. So we can definitively say that R4 is four-dimensional. It has a basis consisting of four elements, the standard basis elements, and we can just write dim of R4 as 4. So it's worth noting that sometimes people will put the word algebraic dimension here, because it turns out you can have weirdo fractional dimensions. There's other ways of measuring dimension. This measurement technique we did was algebraic in nature, hence the name. And as a final point for today, let's note that we know the empty set is a linearly independent set, and its span is the trivial vector space consisting of just the additive identity. So we can definitively say that this is a zero-dimensional vector space and has a basis consisting of no elements. Ooh. And this is nice to have, and again, we want these sort of extremal cases taken care of. And as we've already sort of seen, the null space being trivial, and thus having zero dimension, is a very important situation, because it gives us that the columns of your matrix are linearly independent. Oh boy, I wonder if there's some big theorem about the dimension of the null space that we're about to talk about. And I may have already mentioned it, because maybe the dimension of the null space is called the nullity of the matrix. Ooh boy. I guess we'll find out next time.